Hi, this is John Gardner, Professor of Mechanical and Biomedical Engineering at Boise State University, and welcome to the second part of Module 3 in Industrial Energy Efficiency Process Cooling. We're continuing to talk about condensers and particularly evaporative condensers. So in the first mini lecture, we looked at how these things operate and how they use the evaporation of water to drive the air around the condensing coils to lower than the outside temperature. So the outside temperature might be 90 degrees, but if it's a fairly dry day, we can evaporate water on the coils or around the coils and drive it from that 90-degree dry bulb temperature towards the wet bulb temperature, and that makes the whole process much more efficient. So it should be obvious, but let's talk about this. The conditions around a condenser are constantly changing because it's the outside air, right? So sometimes it's warmer, sometimes it's cooler. If we have the evaporation going on, we can actually drive it below the temperature of the outside air. And as we talked about in the last lecture, the amount of heat that gets rejected is dependent on the outside air temperature and the difference between that and the temperature in the refrigerant and the amount of air that's flowing through it and that sort of thing. So for a given amount of heat, and a certain delta T is good enough to drive our heat transfer process, that means as it gets cooler outside, then the temperature of the refrigerant in the condenser can also cool down. And what that means is it doesn't have to be as high a pressure, and lower pressure takes less energy to achieve. So that's the core of the energy efficiency opportunity, and why we're looking at this is that we want to be able to allow the facility to control their system so that discharge pressure isn't always at a constant value. And so we want to have some basis to do an analysis on, and what we do in the energy modeling field is look to something the Department of Energy puts together called the typical meteorological year. So for nearly every location, anybody that reports weather in the country, they've built these TMY files, and they're hourly temperature data. In fact, it's hourly weather data: temperature, humidity, how much sun was there, and it's real observations for every hour throughout the year. So it's a file with 8,760 entries in it. It's a spreadsheet, so it's records, 8,760 records. And what they do is they look over a 30-year period, and they ask themselves which month of that 30-year period was most typical. What typified the weather for, what's the most normal January for Boise, for example? And they look at those 30 years and say which one was best on that. And they had a very rigorous statistical way of coming to that conclusion, and that became the month they put in the typical meteorological year file. And then they went to February and say, okay, what's the most typical February? And it was probably a different year than what the most typical January was. And so the other thing they did was kind of look at for a couple days before and after and sort of smooth that transition, so you don't have these odd jumps between a January 31st of one year and a February 1st of another year. And so these files are readily available. They're on the National Renewable Energy Lab website. Here's the link. And if you go there and say, hey, I want to look at Seattle, right, you get a file that looks like this. Very busy, and in fact, you can see it's just a small portion of the entire file. And it starts with a little bit of header information and says, okay, January 1st, the hour ending at 1 a.m., here's all the information, right? And this is mostly, there's a manual that tells you what each one of these columns means, but if you scroll to the right a little bit, quite a bit, so we're over into past the alphabet, and we're now into columns A, B, and so on. We have the dry bulb temperature as observed, the dew point temperature, and the relative humidity. Okay, and so any two of those is enough to give us the wet bulb temperature, but alas, the wet bulb temperature doesn't happen there, right? But we can find it. And so I kind of poked around a little bit, and I think these guys who wrote this paper in 2011 gave us a pretty good way of doing this. So not surprisingly, this is exactly what we're looking for, right? Wet bulb temperature from relative humidity and air temperature. And so I just took this excerpt from the paper. This is the meat of the paper. It's this equation. It's a curve fit where TW is the wet bulb temperature, T is the dry bulb temperature, and RH is the relative humidity. And I have this expert here to tell you exactly how to use it. In other words, relative humidity is entered as a number between 0 and 100, not between 0 and 1. And it's in centigrade, and all that matters. Arctangent is in radians. And it's kind of ugly, but it works. Okay, and of course, it's in a spreadsheet anyway, so you only have to enter it in once. Make a column, put it anywhere you want in one of those files between wet bulb and between dry bulb and dew point or anywhere around there. Replace dew point with it, and then once it's in the spreadsheet, now you can use Excel's capability to build a histogram. So we're going to talk a little bit about how this applies, and we'll use as an example data for Kodiak, Alaska. We visited there in the summer of 2013, and I went through this process for the TMY file for Alaska, pulled it out, added a column for wet bulb temperature, and then did a histogram on it. And so what we found here, for a typical meteorological year, the wet bulb temperature in Alaska was between 30 and 35 degrees for about 3,300 hours of the year. So well over a third, close to half. And then another 1,700 hours a year at 36 to 40, and so on. And so you can see it was pretty mild, right? The wet bulb temperature never went above 65, never went above 65 degrees. So this is the information that we can use to verify and to assess some recommendations. So what does it mean for the condenser to be operating efficiently? Well, we've talked about this a couple times. We touched on it at the end of the last lecture. And the idea here is to let the discharge pressure of the compressors float in such a way that it always kind of finds the right equilibrium point by the way the temperature and the pressures are interacting, rather than by a control system on the compressor. And let it float to a certain number of degrees above the wet bulb temperature. Now that said, all of these systems have a certain minimum pressure that they must get to for a number of reasons. And these are the most obvious ones. The expansion valve, the device that lets the refrigerant go from a hot gas to a very cold, saturated mixture, sometimes needs a certain minimum pressure to work right. These big food processing systems use something called hot gas defrost, so they've actually duct the valve in the hot vapor coming off the compressors back through the evaporator coils to melt the ice. Or sometimes they use some liquid, they expand some of the fluid coming off of the compressors to back into the compressor to cool them, and they need a certain minimum pressure. All those things are areas that you have to really assess on site. But let's see why it's worth it, right? So let's take a look at this. So this place we visited in 2013 kept their discharge pressure at about 145 psi gauge, or about 160 psi absolute. So based on what I knew about the system, I did a parametric study saying that if we change the discharge pressure, how does the amount of energy we require to do the same amount of refrigeration, how does that change? Okay, so we did it on a basis of tons, consumption of energy per ton of refrigeration capacity. And we found a fairly linear line. In fact, absolutely linear. So on the right hand side, that point there is 160. That's the normal operating conditions. And so for every way we drop it down, it drops the amount of energy required, and on this axis is horsepower per 100 ton. It drops it quite a bit, right? So it's worth getting into. So let's combine that little parametric study with the weather station, right? With the weather data. So we can, and let's just assume that the temperature that we need in the condenser is 20 degrees above the wet bulb temperature. Okay, so that combines a couple things. The evaporative condensers don't quite get all the way to wet bulb. 20 degree approach is a little on the high side, so I think between the two of them, that's still pretty good. Don't worry about sub-freezing wet bulb temperatures. It's not a feasible outcome, and it turns out we have a minimum pressure we'll set anyway, so we'll take care of that. And we'll assume 24/7 operation, which is typical of a food processing plant. So the scenario is this: system's currently running at 160 psi. We want to see what it would take, how much energy it'll save if we go to a floating head. It's called a floating head pressure. So here's the base case, right? 160 psi all the time. From our little discharge pressure study, we said that that's 1.82 horsepower per ton. There's the horsepower conversion ratio. We're going to assume a compressor motor efficiency of about 90%. That's a little on the high side, but that is conservative for this analysis. 8,760 hours in a year, so it's 13,215 kilowatt hours per ton year of refrigeration. And these are, often big operations. So let's say it's 500 tons of refrigeration capacity. So we estimate that uses about 6 million kilowatt hours, 6.6 million kilowatt hours in a year. So pretty soon that adds up, right? And then this is the meat of the analysis. What we have here is the first column are the bins we talked about, from below 35 up to 65, and then we added 20 degrees to that, right? So that's the discharge temperature of the vapor leaving the compressor, right? Or the saturation temperature of the vapor leaving the compressor. And so for ammonium, which is what this system was, this column, the pressure, it's the saturation pressure at that temperature. And then we apply a minimum pressure. So for example, most of them have to have some kind of minimum pressure. And 120 psi is not uncommon. So I said, okay, 120 psi is the minimum. So the target discharge pressure is where we'd like to be, but sometimes it can't be that low. So we put it, so if it's below 120 in that column, we put 120 in this column. And then when you get up into the 46 to 50 degrees, the target pressure is higher, right? But it's still not 160. It wasn't until this last little bit that it was 166. It needed to be a little bit higher than the 160 psi that it was running at. These are the hours of operation coming from the histogram we just looked at. And there's the horsepower per ton column from our parametric study. So you combine those two things and say that it's 115,000 kilowatt hours per ton year. So again, for our 500 ton load, that means it's only 5,750,000 kilowatt hours used over the year. So that's a savings of nearly 1 million kilowatt hours. And for an electric rate of, say, 10 cents a kilowatt hour, which is not uncommon for the East and certainly in Alaska, that saves $85,000 a year. If it's half that, it's still $4,200, $4,300, $43,000 a year for changing a setting on your system. Okay, so it's a kind of a no-brainer, and yet not many people do this. And that's because these systems can be a little finicky, and there's other things that can go wrong if you're not careful. So we talked about cooling. They sometimes do liquid injection cooling for the compressors. We talked about hot gas defrost. These are all things that you need to check into and talk to the operators about. And basically, it's something you got to keep on top of. You got to make sure it's still working. It takes time. So the main expense is technician time. They probably need to bring in an outside technician for a day to do this, to make sure it's working right. So that could be a couple $1,000s easy. Okay, so but the point of this was to actually come up with a process to come up with that energy savings, right? So I'm going to ask you to take in the problem set for this section. I'm going to ask you to take that analysis I did, that horsepower per ton analysis, and do an analysis like this. Assume the approach is 20 degrees. Start with a baseline of 150 psi for discharge pressure, and then the homework assignment, the problem set, tells you which city to use the TMY data for, and go ahead and do that analysis. So that's it. Good luck with this and the quiz, and we'll see you soon.